Hello, Pradeep, I am audible. Hello.
Yes, sir, you're audible.
Okay, okay. We'll start within 5 minutes.
That's
Let's wait for another participant.
yeah.
Okay, we'll start. Now I'm audible. Francis,
Yeah,
Pradeep, anyone
you're,
tell?
yeah,
Okay,
yeah.
Yes, sir.
okay, okay. I think we will start. So today is I'm going to solve the week 9 fluid mechanics previous year questions. Actually, the week 9 was about the differential analysis of fluid flow, and I think week 10 was also about the differential analysis of fluid flow. That's why here written the week 9 is the differential analysis of fluid flow first. And in the week 9, 4 lecture was covered. Lecture 1 was about the mass conservation equation. You know all the continuity equation, but how we can derive, there are several methods. We'll discuss in this session also methods and concept as well as question answer also. The lecture 2 was about the mass conservation equation second, and lecture third was about the stream function, and fourth one is the causing equation. So the first question is about, I think question is visible to all of you. Please.
Yeah, variable.
Okay. The first question is about, let me A flow has parallel curved streamlines, that is the streamline having the curve and parallel, and is steady, and flow is steady. Thus the flow has a first option is the tangential convective acceleration, B1 is the local acceleration, and C1 is the normal convective as well as the local acceleration, and D1 is the normal convective acceleration. Which one option is the correct? Please give your comment in the chat box. So basically the straight we have discussed earlier about the streamline questions in a straight, and I think one day I have also tell about the curved streamline to all. So please remember that thing and give the answer of the first question. Which acceleration will be okay? Pradeep is telling the tangential convective acceleration. Okay, normal as well as the local acceleration. You please see the question frame. The question concept: a flow has a parallel curved streamline and is steady. Steady means there is no change in velocity with respect to time. So if you remember the equation of acceleration, you can easily give the answer of this question. Okay, let me discuss about the question. Actually, you know, the steady flow means what? Yes.
Independent of time.
Okay. Please. The question one. I think one new student is joined. So, uh, please read the first question and give your answer in the comment box. Two students already given the answer of the first question. First, Pradeep is telling the option A is correct, and Francis is telling option D is correct. And what about your uh, answer about the first question? Option yes, please write your answer in the chat box. Then I will move on the solution part. You write within 1 minute. Then I will just this thing is covered already in the acceleration part, streamline and acceleration kind of thing. Okay, now I want to move on solution part. So basically, you know the here the term is written the study. It is visible whatever I am writing.
Yes, sir, pretty good. Visual.
Okay. So steady means what? The change in, let's say, for fluid proper fluid parameters, I am considering the velocity. The change in velocity with respect to time is equal to 0 in case of steady flow. And you all know the acceleration, let's say right in the x direction, what will be the local acceleration as well as convective acceleration. Convective acceleration. So local acceleration is represented by the time, that is velocity with respect to time plus this represented by, you all know, w du by dz. So this is the definition of actually mathematical definition of acceleration. So in the fluid flow, so already here written the study, so this term is 0, that is the local acceleration is 0. So option B and option C both having the acceleration, local acceleration, so this is wrong. Only remaining thing is normal convective acceleration and the tangential convective acceleration. Let us discuss about both acceleration, what is tangential and what is normal acceleration. So let's say the velocity is flowing like that, that is the streamline. This is the streamline, and a fluid particle is there. If we try to measure the velocity of fluid particle, let's say the direction of this, so velocity in that direction and velocity in that direction, let's say the u and v, that is a component of velocity. So streamline, actually what gives streamlines is give the, if you draw the tangent on a streamline, it gives the velocity. It draw the tangent on the streamline, it gives the velocity vector. That means the component of both, that is the, actually I want to draw again here, the velocity vector, and this one is a u component and this one is a y component, that is a v. So in the question is already given one thing, this thing represent the tangential acceleration and this thing represent the normal acceleration, normal convective acceleration, because convective means it changes with the position, the acceleration change with positions. So convective acceleration is this. So in the question is given the parallel curved streamline, that is if the streamline is straight, only there is no another component of the velocity. If the parallel streamline is like that, there is no component of the velocity, only one component. But if the velocity streamline is like that, that is the curve or parallel, or so here the velocity having the component, two component, one is the tangential, and if draw the here, one is the tangential and another one is normal. If you draw the tangent here, what will, your direction is like that, your u direction is constant, that is the in the direction of a streamline, but v direction is changing when you draw the streamline. If you draw a streamline here, what will happen, this is the u and this is a v, that is the normal component. So your v is changing in the curve surface, on the curved surface. So here, that is the no acceleration exists in the tangential direction, but in the normal direction the acceleration will be exist. So option D will be correct for this question, and I have discussed description about this question in a very normal way. If you read here, I think everyone got the concept behind it, why the normal acceleration, normal convective acceleration is correct answer for this question. If you not get, please read this statement, then we'll discuss again. So let us read. This is a very, very important concept. So what is written, point wise we'll discuss. The normal convective acceleration arises when there is a change in velocity of fluid particle. There is change in velocity of fluid particle in the normal perpendicular to the streamline, whatever I was discussed. If you draw the here, then what is the tangential, and this one is the your normal. If you draw here, this is the, and this is the tangential velocity, and this one is the normal velocity. Good. So velocity is changing, that is in this direction velocity, at that point direction was changed, at that point maybe the direction was this one, this side for the normal. So perpendicular of the streamline, that is thing here written. The normal convective acceleration arises when there is a change in velocity of fluid particle in the direction normal, that is a perpendicular to streamline. Okay. In the case of equidistance means parallel equidistance curved line, curved streamline. The key factor is that the streamline are uniformly spaced apart. Okay, so this is the written. When streamlines are uniformly spaced and curved, it means that the fluid particles are not only changing their velocity tangentially along the streamline, but also moving closer together or farther apart as they follow the curved path. Okay, like you, okay, we'll discuss. And this change in spacing between the particle in the normal direction causes the change in their relative velocities. As a result, there is a normal convective acceleration in such a flow field. Okay, let me discuss very simple way. What is this? In simply, if we say, when you have a curved streamline that are equidistant, if you have the equidistance curved line, there is a change in speed of the fluid perpendicular to those curves, and that's why we have the convective acceleration. One line is also here written. In summary, if we tell, when the streamline are curved and equidistant, there will be a normal convective acceleration because of the fluid particle are changing their velocity in both tangential and normal direction as they follow the curve and eventually spaced streamline. So here the concept is that if the streamline is curved, the main concept is similar. If I again repeat you, if these are the streamline, and you remember one thing also, when if we talk about one road is there, like curved road, when the vehicle is passes from, let's say, the curve, what will happen, you all know, this try to push up this direction. So let's say the fluid particle is moving here, so this force due to this centrifugal, so particle, the force try to move the fluid particle towards, so that is why the fluctuation in the normal direction. So normal convective acceleration will be correct answer for this question. So please,
So can saying
yes,
that the tangential component vanishes.
yes,
Why the tangential component vanishes here?
tangential component is vanished because of you, what I am discussing. If you are let's say the streamline is curved streamline. What is here written? If you see, in a simple term, when you have the curve streamline that are equidistant, okay, there is change in the speed of fluid particle to those curve, and that's why you just think on that line there is a change in speed of fluid particle to those curves. Whatever the curve is here, let's say the I want to draw the curve.
So I understand why there is a normal component of acceleration, but actually the horizontal component of velocity is also changing, isn't it? When we take different points, the u will be different. Horizontal velocity of u will be different, isn't it?
Yes, what you are telling, please again tell. Francis, you again tell about your.
I understood why there is a normal component of acceleration, but for the horizontal component, I mean the tangential component is also changing for the different points, isn't it? The u will be different points, isn't it? Different. So there is a tangential change in the velocity also happening there. So there should be a tangential acceleration, isn't it?
No, actually, if we talk about the streamline curve streamline, only the normal convective acceleration is reason behind it. Whatever I have discussed, the velocity. If you take the streamline is definition is that if you take the any tangent along the streamline, what will happen? Uh, that it gives the velocity vector. Your velocity along the streamline, if you draw the here the this is the direction, streamwise direction velocity, and this one is the your velocity is u velocity, that is a v velocity.
So we are actually resolving the component through that streamline.
Yes. So
Okay.
yeah, that is the reason only the normal component, only normal convective acceleration is here. Okay, I will discuss more about it. If you want, I am getting what is going in your mind. Okay, I will discuss more on that. No problem. What you are thinking, I am getting. So if but basic reason is that if you resolving the component along the streamline, your velocity in the normal direction is changing with respect to. So that's why the normal component is the correct answer for this question. So if you see the question number two is very easy question. The the flow of a liquid at a constant rate. Constant rate means Q is equal to constant. There is no change with respect to time. In a conical tapered pipe, let's say the pipe is like that, conical tapered. Conical tapered pipe is classified as what? This is a steady or uniform flow, a steady or non-uniform flow, and a steady or non-uniform flow, and a steady unsteady. Option C is unsteady uniform flow, and option D is unsteady non-uniform flow. So as you have learned lots of things in the fluid mechanics, please based on that concept you write your answer in the chat box for question number 2. Okay, for question number 2, Pradeep is telling option B is correct. Okay. Yes, another student also, you if you want to write your answer in the chat box, you can write. Just open your message box and you can write your answer, whatever you have understand. Because when the final exam of this fluid mechanics course, when was the time?
So 28th of October,
20 October,
28th, 28th of
28
October.
October, or I think on 20, I think on 18, I will finish the all 12 week of this question, and one after this 18 October, on maybe on, if you are ready on 19, I can take 1 hour summary class about which type of question might be come on your final exam, and the whatever your questions like doubts will discuss on that day. 1 hour class, not more than 1 hour. So maybe on 19, or if you ready for next Monday, we'll take on next Monday, that is on I think 23 October. But up to the 18 October, I will finish the all 12 weeks questions. Okay,
Thank you.
so
Thank you.
Palak, I think if you want to give your answer, you're right. Okay, by the way, option number B is correct, study and non-uniform, because study, you know already, the rate is constant, so study, and definitely non-uniform flow will be the because of the conical kind of thing. Okay, there is a lots of concept today I have discussed these things also. I think Francis, your
So,
question was about, yes,
so, so in the first question, actually we talked only about the A axis in it. There should be an AY and AZ. So why we are not considering that A other A components? They should be perpendicular to the A axis in it.
yes, what you are telling?
I mean, here we only talked about the AX component, isn't it?
No, 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 no. Just AX I have given only for you. You don't relate this. I have AX given only for you. The acceleration component is having two things, local and convective. Okay. You don't think this, right? Here, uh, actually, uh, why I was given AX, because of the, just you saw the acceleration is having two things, the local and convective acceleration. So there is no meaning here the AX, just for conceptual, what the
Uh,
concept behind the normal acceleration and this only I have discussed.
so, but we when we take that total derivative, we are getting AX, AY, and AZ, isn't it?
Yes, if you want to the total acceleration, AX, that is the under root of, let me write on another here. If you want to the acceleration, total acceleration, what will be there? AX square, AY square, and AZ square. So this is the
So,
total acceleration. But here only which acceleration in the, if you are talking about curved streamline.
so this AY and AZ, we didn't tell anything about this AY and AZ, isn't it? In the previous question, there was a previous question that we did in earlier week also. We didn't mention this AY and AZ, and we only considered that AX only for this streamline condition. So, is there anything like that? There won't be any AY and AZ for
No,
streamline.
no, actually your AX represent the AX. Actually, the question I think you have might confuse from here. The tangential means, if you notice, the tangential acceleration means what? The flow along the streamline, that is the this acceleration. But in your question is already written here, the flow is steady. You all know the flow is steady means the flow at a particular time there is no change. If you, let's say that at 8 a.m. you are going to measure at a particular throughout your at a particular cross section, if you are going to measure, let's say the pipe is bending, let me draw on this, that is let's say that this is the curved pipe and water is flowing like that. So steady means what? Your velocity is not changing with respect to time. That is, the velocity is constant with respect to time at a particular cross section. But the acceleration in case of the fluid, we have measured the both at a time. But in case of the fluid mechanics, acceleration is a component of with respect to, we measure the acceleration with respect to a space as well as time. So here, due to the steady thing, the time velocity, that is the time acceleration is zero. That is the local acceleration is zero, but convective will be the exist in all cases. Oh, Francis.
Yes, sir.
Okay, Francis, if you are want more discussion on that, we'll discuss, no doubt. We'll discuss in the next class on that.
Okay, sir.
Your doubt, I am okay. So I think, okay, now I think your question was about the pitot tube. I think I have seen your question, your doubt, Francis.
Yes, sir.
Your question was, one question was about the pitot tube, right?
Yes, sir.
So I have seen only one question, and uh, I will discuss all your doubt in the coming classes, no doubt. But today we'll discuss about the pitot tube concept, right?
Okay, sir.
Okay, and if you want, let me discuss. Then after, first let me discuss. Then after we'll go for the another. So pitot tube concept is nothing but, let me discuss. That is the pitot tube and probe is a name. First, what was happening? The Henry Pitot, and another engineer was about the Darcy's, Henry Darcy's. Henry Darcy's. Actually, the concept of pitot static tube was given by this guy, this engineer, and pitot tube concept was given by Pitot, Henry Pitot. Okay, only pitot means what? L shape. Right. But if you are talking about the pitot static tube, probe, everything is same. Yes. This is the same thing, but one thing is extra here. When another pipe inside the pitot tube also. This is connected with this. Okay, and here the perforated, that is the small openings around the circumferences. What you have seen here, this is the, okay. So this kind of thing on the static pitot tube. This is given by the Henry Darcy's, and this is given by this thing. Only measure what? Or the stagnant. stagnant pressure, and this thing is measure both stagnant and static pressure difference, right? So you know the already the stagnant pressure is what? The P static plus rho V square by 2. If you calculate from here the velocity, so P stagnant minus P static divided by rho, you can multiply. This is your velocity. The working principle is that your pitot tube will calculate your if you want to calculate here, how will calculate the static pressure? Piezometer is there, one piezometer. This piezometer will calculate the static pressure. So from first, if you go before the pitot static tube concept, we use both things, piezometer and pitot tube. But after this concept, we use only one thing, and this pipe is connected with the this pipe. This pipe is connected with some pressure measuring instrument, and here is the pressure is coming also, and this pipe is also connecting with this, and here the pressure measurement difference is calculated. So this is the whole concept behind it. But one thing is very important. Here the P static means is not that the P static, because if you see in the pipe fluid is moving. If term is like that P static means not the pressure, the water in or liquid in rest or gas in rest. So P static means that. Anyone else? Anyone telling something or not? Okay, this is the P static concept is very important. If fluid is moving or rest, in both cases P static will exist. How? Let's say this is a pipe flow. Pipe flow means what? This is a pressurized flow. Pressurized flow. That is your fluid particle having the pressure. This fluid particle imparting the force throughout your circumference of your channel. That is your pipe. And also, so due to this pressure, due to this pressurized flow, what will happen? If you insert here your piezometer, due to this pressure, due to the pressurized flow because of in a pipe, what will happen? Your fluid in this pipe will increase, let's say up to the H height. So this thing is give the static head. But if you want to calculate at a static head at that location, what will happen? So you know the hydrostatic concept, the rho of the fluid density is rho. So use the rho gh. Let's say the point 2. The static pressure at point 2, that is SP, static pressure at point 2, what will rho gh, or let's say this is the capital H, this is capital H at point 2. So a static pressure is not mean that if your fluid is moving, so there is not exist of the static pressure. Static pressure is there due to the reason behind it, because in the pipe pressurized flow is flowing. So that is the, so if if you summarize these things, your static pressure is the combination of both things. What your due to the pressurized, the pressure due to the pressurized flow and the hydrostatic pressure. If we talk about something, let me, if we talk about in the open channel case, let's say this is the bottom. If flow is not pressurized, what will happen if you put the piezometer, let's say, on the free surface, and you here come, this is the your fasteners holding the piezometer. So there is no increase of the fluid. There is no increase in the piezometer. If you put on the free surface piezometer, free surface on the, if you put the piezometer on the free surface in case of open channel flow, there is no height increase in the piezometer. So here, because why? Because the pressurized flow is not here. But if you want to calculate the pressure here, then the same concept hydrostatic, if the height is this, then what will happen? Rho gh. So your static pressure is what? Static pressure is this. How much height in this? There is no height, so 0 plus rho gh. So in case of open channel flow, your static pressure is same as the hydrostatic pressure. But in case of pressurized flow, there is a bit difference. So you never, you always remember, if the fluid is moving or whatever is standing, there is no uh, static pressure will always exist. Or the reason behind it, in case of pipe flow, the pressurized flow, because of the fluid particle forcing on the wall, forcing on the acting force on the wall. So the concept of pitot tube, let's discuss here how the pitot tube is work. First, previously how pitot tube was working and currently how it is working. So for static, let's say the pipe, pressurized pipe flow, and here is the pitot tube. P2. So what will happen if your fluid is not moving? Let's say fluid is not moving, so height in this and height in this will be the equal. But as fluid is moving, what will happen? The your velocity is coming here, and velocity at that point will be 0, and that kinetic energy is converted in this form, and it will increases here. Your height will be increases at that point. So if you measure from that location to that location is known as hydrostagnant pressure, and only this height is known as the static pressure, or here also static pressure. So this is the concept. But after uh, static pitot tube, what is happening? After static pitot tube, let's say I want to draw again. Okay, this is connected, this is your original previous one pitot tube, whatever is Henry pitot was developed, but Darcy's what done here, the perforated kind of thing at that throughout the circumference. So due to the velocity, the same thing principle is same happening here also, and this thing is connected with your pressure measuring device. Let's say the one, this is the device, and this is will connect with this. So drawing is not good, but for your concept I think you are getting if you are looking the very precisely. So what is happening due to this, actually your perforated, your water is flowing like that. So your perforation is the perpendicular of the streamline. So there is your perforation, whatever is here, a liquid is entering in this, there is no effect on velocity. So perforated part is measuring the static things, and here your whatever is opening is there, it is directly contact with your velocity, that is your streamline. So it is measure what? It is measure because fluid is also entering in this, so static is definitely there, but velocity effect also on the pitot tube. So static as well as velocity effect both are on the pitot tube, so that's why it measure the both things. And perforated things, there is no effect on velocity, so it is measure only the uh, it is measure only the static things. So here you can use the manometer also, we can use manometer. These two pipes are connected with the manometer, and one is, let's say one pipe is for pitot tube, another pipe is the perforated pipe is there, that thing is connected here, let's say the connected, and the mercury is there, and when the pressure is here, the difference of the let's say mercury is increasing on that, so difference on this height, so easily we can measure like that. The whole concept behind the pitot tube is that. I think Francis, your doubt is clear on that. Hello Francis. What is a static pitot tube and pitot tube, and how it measure static pitot tube and how measure the pitot tube? I think you have clear.
Yes, sir, understood.
Okay.
But that there was a statement like the uh, pressure will be dropping. There was rho g z component in that the last class, isn't it? And you said that the it is not like the ordinary rho gh, and it will be decreasing with respect to datum.
Okay. Now I'm getting that thing. I will also discuss. No problem. This is a very, very important doubt. No issue. I will discuss again. So that you already know one thing. The hydrostatic pressure. Let's say one tank is there, and if you want to measure, let's say the point P1 and point P2, and height is this H1, and this one is H2. So P1 is what? If the density is rho G H1, and P2 is what? Rho G H2, H1 plus H2. So definitely, as height is what is here. Okay, let me compare another thing. And one, and you know the Bernoulli equation is what? P by rho z plus V1 square by 2z plus Z1 P2 is square by rho g plus V2 is square by 2g plus Z2. So this is the Bernoulli equation. So here is what happening. as your height is increasing, let's say the at here height was 0, but at that point height is h1 plus h2, your pressure is increasing with the height in case of hydrostatic pressure. But here, let's say the your you are going to apply this z term is representing what? This is the datum thing representing. Let's say I have taken the datum from here. So what will happen? Let's say I want to this is the z1. Let's say I want to draw here again. This is the pipe, and I have taken the datum at that location. So this is the z1 and this is the z2. Okay, but I can also take the z. But if you calculate the P1 from here, what will happen? Let's say the pressure P by rho Z, if you want to calculate, everything will remain same. P2 by rho G plus V2 square by 2G plus Z2 minus Z1. Z2 minus Z1 minus V1 square by 2G. Okay, no issue. So here is these things. If you want to take the datum, let's say some little bit above, let's say here if you want to take the datum, so here Z is equal to 0 and Z2 is equal to what? Let's say something. So this thing is depend on what? Your Bernoulli's equation, that is your static pressure, only whatever here you going to use this pressure. So what was your statement? The pressure was decreasing with respect to here, as your height is increasing, your pressure is increasing. But here as height you're increasing, what will happen? Your pressure will decrease. So this statement was about the streamline, not that term was written for not your in terms of that is the that statement was about the you cannot correlate. Actually, if we talk very specifically, you cannot correlate these things, the hydrostatic pressure and whatever your the reference thing, that is the your jet only depend on where you are going to take the reference, where you are going to take the datum. So you cannot that statement was telling that your hydrostatic pressure you cannot relate with the, because one I think that was P is equal to rho G Z. This term was coming on that player what where you are talking. So this thing you cannot correlate with the hydrostatic pressure, because term is similar here also, rho G H. Rho G here H and here Z. This is height also, this is height also. But hydrostatic pressure is decreasing with respect to time, with increasing when your height is increasing towards the downward. But this thing you cannot correlate with the this is the different and this thing is different, because as you know I have was discussed, that is the in the Bernoulli equation what is P represent? P actually represent your stagnant kind of thing, stagnant pressure. because you know the concept. If you're talking about the fluid your diffuser, you know the diffuser kind of thing. Let me discuss first. If the such kind of pipe is there, and let's say the P1, P2, not P2, P1, V1, P2, V2, P2, V2, and one pipe is like that. This is the P1, V1, P2, V2. So if particle is moving from here to here, and here also the particle is like that. So it means what? If particle is moving towards the from this side to this side, let's say here your pressure is this side to this side. If particle is moving, the P1, in that case what will happen? The P1 will be the greater than P2, and V1 will be V2. These combined thing, what is showing? These combined thing is showing the your stagnant pressure, stagnant, not only the static. So you always remember, if you talking about this example, what will happen if diffuser, this I think in the mechanical engineering this is very useful, the diffuser. So your particle is moving like that. So in that case what is happening here, your static pressure P1 is actually, in that case what is happening, P1 is less than P2 static pressure. But when you compare the stagnant pressure, P1 at stagnant at 1 is greater than P2 stagnant. So you always remember, we always, when the particle is moving from one side to another, we talk about the stagnant pressure. Not only we talk the static uh, kind of thing. So Francis, your question was about the this thing. So this jet was correlated with the datum thing. As you shift the datum as per your dependency, as you shift the datum from above or down, the pressure will difference. But you cannot relate with the hydrostatic pressure. That statement was that thing all, not much concept on that.
Okay, sir.
So our today discussion was about the differential analysis of fluid flow. So in this chapter we'll continuity equation definitely will see, and continuity equation is nothing but you all know the conservation of mass, and the Newton's second law was about the Navier-Stokes equation. So I think Navier-Stokes equation was done or not in your class?
No, don't sir, briefly done, not much.
Okay. Here I will just I will show you how can we calculate. Uh, Actually, if we can take a 5 minute break, I think, is it okay?
Yes, sir, that will be great.
Yes, we can take the 5 minute
Yes, sir.
break. Then after we'll continue.
Sure.
हेलो. हाँ नाना के. ना बोलता था कि उचियावी के जन मामा के लिए क्या होगी और जगह बारिश हो रही है एक बार. हाँ हाँ एक बार मिला के बात किए ना आप. अच्छा अच्छा ठीक ठीक है बात कर रहे हैं हम क्लास में नहीं अब यार हम बात ही नहीं करनी. हाँ. हेलो. हेलो.
Yes, sir.
Okay. So in this basically further we are going to just I will discuss about some concepts, not much. So actually this thing is very important because before going on the much discussion that is on conservation of mass and conservation of momentum and how can be derived, so it is very important to understand why we are going to actually how can approach the problem. So we have lots of things written here. If you want take the screenshot you can take and read. Please Francis, if you want to take the screenshot you can take and read.
Yes, sir.
Actually it will help you for understanding the why we are differential analysis of fluid flow. Actually this is very important because the motivation is very important for study any topic. So these things give you motivation. You can take this screenshot also of this. Here the Pradeep, you are here or not? Pradeep, I think here not here. Okay.
No, I'm here, sir. Yeah,
Okay, you can take screenshot also, Pradeep. It
I
will
can, sir.
help. It will very helpful for you.
I can, sir. Yeah.
Now I am going to first you take screenshot of
No,
this.
I've taken, sir. I was there actually, sir.
Okay. You take screenshot of this also. So now the conservation of mass things is that here is very important because sometimes I was confused why the Renault transport theorem, but this in this book very well explained from the very basics where we can Actually, I was I was very confused where we are going to use the Renault transport, because in the several books not given like that. So what is written here? Let's read. Though the application of Renault's transport theorem in chapter 4 we have already, I think in your lecture number 4 you have already, we have the following general expression for the conservation mass as applied in the control volume. If you are going to apply the conservation mass on the control volume as per the Renault transport theorem is what? Change in, actually this is 0 is why you already know why it is 0. So basically change in mass with respect to, I think this thing was there, change in mass this with respect to the time. So it is 0. So control volume and these things. Recall the from equation 9(1), it is valid for both fixed and moving control volume. This equation is valid for both fixed and moving control volume, provided that the velocity vector is the absolute velocity as seen by the fixed observer when there is a well defined inlet and outlet. If it is a well defined outlet, the equation uh, 9.1 is written like that. So it is written like that, these things. If you take the this side, some minus. So this is the change in density with respect to time or with respect control volume. So mass in and mass out, basically nothing but this is the mass balance kind of thing, you know already. The mass in and mass out is equal to something storage. So this concept is derived from that point. But if you are going to apply something in case of uh, not, in other words, what is written? In other words, the net rate of change of mass within the control volume is equal to the rate at which mass flow into the control volume minus the rate at which the mass out in the control volume. Actually, this is written very well. The net rate of change of mass, actually how much mass, what is the rate of change of mass in this control volume? It depends on what? What is entering and what is out, which rate is entering and from which rate, by which rate it is going outside. So this is depend on that. So this is nothing. And another thing, derivation, actually the here in this book I have find also one very important thing. The conservation of mass actually derived with the uh, different approach. First was derivation using the divergence theorem. Actually this derivation of the conservation of mass using the divergence theorem, and this is the final equation by the divergence. The equation is same in the every approach. Using the derivation, after discussion you I will show you, you can take screenshot, no problem. Derivation using the infinitesimal control volume, that is the control volume approach, is also given for calculating the same equation for continuity equation. So this is the final equation using the control volume approach. So this is the equation in the Cartesian coordinate. So alternative form of the continuity equation, this is the, there is no, the previous what we have discussed, the same thing is written here. The special case, if the flow is your steady, then what will happen? Your t term will be the, if this is your alternative form of the continuity equation, if you see, if the steady flow, this t term will be the 0. So that's written here only. Okay. If you will write in the Cartesian coordinate, this equation is look like that. If its flow is your incompressible, then rho is also outside. So what is remaining? Only du by dx. You are very familiar with this equation, I think. dw by dz. So you are familiar with this. So the assumption behind this form, what is the steady as well as incompressible. Okay. Okay, here is written the incompressible. No, this is the equation is written what I was discuss.
So,
Yes.
here the only the variation with the temperature is time is only taken with respect to the density, isn't it? Why we are not considering the in the continuity equation?
In this equation?
In the continuity equation, actually the density is actually relation with the density with respect to time is given using the first term, and the second term is actually only with respect to the coordinates, isn't it?
Yes, yes, yes.
But we are neglecting the difference with the time for that velocity term. Uh,
No, no, no. If you see the, okay, no problem. If you see your Reynolds transport theorem, what is given? Actually, your all equations was what were the fundamental equations was derived for what the system actually. If you talk the rigid kind of thing, there is no inside flow and outside is going out. For that type of problems, your basics law was not derived, but using the Reynolds, that is Reynolds was researcher and give these things. You can using this concept. This is rho. If you look very what is written here, this is only written mass. If you see these things, that is the rho is equal to kg per meter cube. T is the time, that is second, and this one is the meter cube, volume is meter cube. So meter cube is cancelled, that is the mass flow rate. This is what is written, this is the mass flow rate or not so mass in, mass out, mass rate. Actually this dot is given for what, mass by time. Mass by time is in, mass by time is out, and what is, how the rate is changing in this. So now we come on that, if apply this concept on, if you are using these things. So I think Francis, your doubt will clear from here also. So for m, if you are going to calculate expression for m in and expression for m out, so it will come on in what, it will come in the terms of, where is written, if you are going to, I think here is explained very well. Yes. So in the control volume, if you are going to something in and something out, it is travel from that point to that point. So distance is varying for in or out. In the case of in and out, the it is varying from the distance. So this is the reason, and actually if you are see this equation, this is also your whatever the mass flow rate, that is the mass by time, mass by time. But you go, when you derive the equation like that, the mass by actually in, mass rate in and mass out, mass rate out. So actually your expression is come like that. So this is the, where is, yes, I think this expression mass, if you see the mass in expression is what, this is the mass in expression. Okay, your mass in expression is expressed like that, that is the, your derivation like that. So and rate of change of mass within the control volume, that is the how the mass is changing in control volume. So this is what d, if you see here, this is also kg per meter cube, rho means kg per meter cube, and time is here, and the dx meter, dy meter. So it is cancelled, and doing the mathematical expression, your final expression is coming like that. Where is, oh, this is the, your final expression is coming like that. The continuity equation in the Cartesian coordinate, your final expression is coming like that. So this is the reason.
Okay.
Yes, the main reason is that this is also written your mass, but this is the volume thing. Here is also dx dy dt, dx dy dt, dx dy dt. So it is cancel out. So that's why look like. And the reason behind it, why t? The t is due to the, you know, the actually the rate of change of mass within the control volume. Your this thing is represent the how the mass is changing in your control volume, and this all things represent what, the in and out things. So now we'll move on the next. Okay, incompressible we have done. The stream function, you know very well. On that I have some questions. The stream function in the Cartesian coordinate. Consider a simple case of the incompressible flow, two-dimensional flow in the xy plane. The continuity equation is like that. Incompressible and a steady flow, if you have, the these things is, your equation is this. A clever variable transformation enables us to write equation 99 in terms of one dependent variable, that is phi, instead of two dependent variable. Here you all know du by dy, or let's say the del u by del y, and so this y thing is represent what? This is the independent thing or y dependent thing? Y is the function of, let's say, u. If you,
Dependent.
yes, your y actually, if this function is like that, it is actually independent. Whatever you will put here, the value will come on y. If you are putting 1, then value is 1. Let's say the expression something like that, the value is x1. If you are putting 2, then let's say the value of y2. So actually based on that value, your value is of y is depend. So this is the independent kind of thing, and this is the dependent. So here is how much that is a dependent variable to u and v. So why stream function is coming in picture? Because of the, we are trying to reduce the independent variable in the equation. So this thing in, that is a dependent variable is written v and w, actually u and v, and we define the stream function as incompressible two-dimensional stream function in the Cartesian coordinate. U is equal to, it is equal to definition of this. You always remember these things, phi by y, and v is equal to minus d psi by dx. So you always need to remember these things. I want to also write here some questions on that.
ನೆಕ್ಸ್ಟ್ ಪೇಪರ್ ಎತ್ಕೋತೀನಿ ನಾನು ಬೇಕು ಬೇರೆ ತಗೊಳ್ಳೋಣ ಇನ್ನೊಂದು ಬಂಡಲ್ ಇದೆಯಾ ಆಯ್ತು
I think someone please unmute. Okay. So the equation is that the stream function equation, u is equal to this and v is equal to this. The stream function and the corresponding velocity potential function we'll discuss, I think, in chapter 10 which is given, where the first introduced by the Italian mathematics Lagrangian, and substitution of this equation, if you put the what will have what will come, if you put u is equal to these things, your equation expression like that here is written. So in this equation, if you see, psi and psi is there, so only one dependent variable. So this is the only mathematics, there is no hard and fast rule. So which is identically satisfy the smooth function, that is the phi is function of xy, because of the uh, order of differential xy, y then x versus x then y. Actually this is not. So you all know that equations of the streamline. The the curve of constant phi are the streamlines of the flow. Actually, before we are moving again, you can take a screenshot from here also. Up to that, I think was done, right? No, up to that. Yes, you can take the screenshot from here. Conservation of mass and continuity. In the last, I was forget. If you take the screenshot, then the derivation, please you go through this and read line by line. Definitely you will understand how we can derive the conservation of mass using the divergence theorem, and you go through the basic. If you don't some sentence and some word, if you don't know technically, so you just google and find out where is the source, where is the origin, so definitely you will get. Now you can take the screenshot this uh, derivation using the control volume you also take, that is the here Taylor series expansion we use. Here you can also take the screenshot for this control volume approach of continuity equation. This is the again you can take for this, you can take also the alternative form of the continuity equation. Now the special case of the continuity equation you can also take. Now the incompressible flow, if flow is the incompressible, then the equation is look like that. Now the stream function is very important. And why stream function? Because of the, you know already, I have tell because it's try to reduce the dependent variable in the equations. And why we are try to reduce the dependent variable? Just google and you can definitely get the clarification on that, because very important. Sometimes the variable is more, and sometimes the variable is more, we cannot solve the equation, so this kind of thing is very helpful. So from here I think one question we can take, then after we'll move. Yes, the question 3 and 4 is visible, please. Question 3 and 4.
Yes, sir, visible.
Yes, please try to solve the question number 3 and 4. Here actually what is given, the potential function, I think also asking. So for the potential function, equation is, I think I have actually in the, this is actually the previous year questions, I think it is. Let me check. Or you try to solve the question number 3. I think everywhere is minus. Yes. If you know these things, I think only the mathematics is remaining here. So using these relations, only your in the equation is given what? Xy, x into y. Now I need these things. What is the phi? So it is mathematics only. You just try. And question 4 is also very, very important. Actually, what is given? You know the velocity having the 3 component, u, v, and w. So here u and v is given, and w you need to find out. What is question number? This is also question number 6 is very, I have solution for this question number 6. Actually the solution of question number 3, let me try also. The question is written phi is equal to x comma y, x into y. Actually, and we need phi is what? So d psi by dy. I think here minus is there. Pradeep, your answer is first, right?
Yes, sir.
For 3. Okay,
Yeah.
and Francis, if you want to give comment, please give, and then I will discuss how we will solve this question. Just within 2 minutes, please. Yes, yes,
I
please
was
give.
stuck with the first one.
Okay, okay. And another participants, please you also give your comment. Okay, now we'll move. So how you will solve this question? Let me explain. Actually, your question is given x is phi is equal to xy, and you know the formula of phi, del psi divided by del y is equal to u. If you put here x comma y and dy, it will be x. So u is equal to x. Now similarly for y, similarly for v. So but here is the minus things. So if you will calculate what is, so this is also v is equal to minus y. You know the potential function is, what is this? Here we will write only 2 because of only xy is given here. So if you want to put how much u is equal to x, so the final equation will become del phi by del x, del phi by del y is equal to, this is minus x and this is y plus y. So if you will integrate these things, so actually only the function of one, that is x, so you can write here d phi is equal to x dx So phi is equal to x square by 2 plus c. Equation 1. That is the minus x. So here minus things. Now phi is equal to what? In the second case, d phi integration y dy. So phi is equal to y square by 2 plus c. You have two equation of phi. Minus x square plus c, and that is a plus y square by 2. Let's say this one is the c1 if you want to write. This is c2. So you people got this expression? Pradeep. Pradeep or Francis, you people got this expression phi and in terms of x and y?
So actually, what I did was first I integrated with that 5x, and I take that c1 as a function of y, and then I try to differentiate it with respect to the y, and I found out the equation of that fy.
Okay, okay. And what about your Pradeep? Please tell. You have got this expression like that,
No,
or
sir,
you?
because I saw a minus, sir, so I saw minus, so because it is said minus, so I just chose that one. I did
Okay,
not.
okay,
So
okay,
I
okay.
So is the dou phi by dou x negative? Actually, the dou phi by dou x is actually positive, isn't it? Is it actually negative? Potential function differential, is it negative?
No, no. You are telling what? If no, no. If you will go with this concept, where we somewhere we have done mistake, or you are telling mistake somewhere I have done, or what you are telling?
Uh, I have a doubt about that formula dou phi by potential function with respect to x. Is it actually positive, or actually it is positive, isn't it? There is a negative at the dou phi.
Is it positive? Actually, let me check again. I have seen. Actually, I have just. Actually, I forgot just by Google out. So I have seen somewhere it is a negative is given. D phi by dx is equal to minus by. It is okay.
It's negative. Okay, sir.
No, no. First one is a d psi by dy dx is equal to negative. It is okay. But for phi, actually this concept should come on the. I think in the next. Yeah, it is okay, I think. But here is written in the positive. No, it is negative. I think Francis, it's okay, no problem.
Okay, sir.
I have seen some 2 or 3 slides. It is negative everywhere.
For the potential function. Okay,
Yes,
sir.
yes. Or otherwise, we will discuss no next class also about this also. So no problem. So when you will combine these things, you will get your the first expression. So the first option is correct for this question. So please, question number again coming on question number 4. Question 4 is visible.
Yes, sir.
Okay, for question number 4, you need to calculate the function of actually z thing, the z component of the velocity. So how you will calculate these 3 things you know already. d phi by just I will, you can take a screenshot and you will solve on your home. You take a screenshot. This is now the next question is this: verify whether the function phi, that is a potential function, is valid potential function or not. You know already these things. One formula, I think Laplace equation, you know. D square plus dou square phi by 2y square should be 0. Let me check. So if you will put here, first you will calculate dou phi by dou x, dou phi by dou y. Oh, here you will get what? I think minus 6x is 6x, right? And for y, that is a 3y square and minus 3x square. And when you will again differentiate, what you will get? Minus 6y. And if you again differentiate these things, you will get minus plus 6y and this is 0. So if you combine these things, minus 6y plus 6y is equal to 0. So you got, so it will be the 0. Pradeep and Francis
Yes, sir. Yes.
and another guy also, Palak. You got the concept of question number 5th?
Not that much, sir, actually.
Okay, okay, no problem. Let me discuss again. So actually what is given, the phi function is given like that: y cube minus 3x square y, and question is written whether this flow is potential function, let me read, valid potential function or not. The condition is that for valid potential function, you integrate this phi 2 times with respect to x and 2 times with respect to y and add both term, and it should be 0. So this is the for valid condition. So actually you will, when dou phi by dou x, first time derivative, y cube minus 3x square y. So how much? The dou phi
So
by
the second terms are the phi square, dy or dy square.
this is y square.
Right. Okay.
So here if you will go, here there is no x term, so this will be 0, and here the x term is there. Let me write and explain by first term, dy dx 3x square y. So this is 0 minus 3x square. If you will differentiate x term, that is the 2x into 3 6 x, and y is remaining. Y is a constant because here the x system is there. So only 6xy. First, if you will again differentiate this term, that is the dou square by dou x. So what will happen? 6 is constant and y is also constant, because here the you are going to differentiate with respect to x. So minus 6y, or only one x there, so 1 into 1, so that is into 1, so minus 6y. Similarly, if you will do for y, that is the dou phi by dou x dou y. Oh, what will happen? Y cube minus 3x square y. If you will differentiate, what you will get, that is the 3y square for this, minus y term is here, so 3x square. But when again you will differentiate y square, what will happen? This 6 y square, and here is no y term, so this will be 0, so only 6y square. So your d square
We are differentiating with where, is it not? With respect to y. It
with
should be
respect to y, yes.
so. It should be 6y. It should be 6y.
How is 6? No, not
Yeah,
y,
6.
only
No, no, no.
6y,
Yeah,
only 6y, not square. Okay, and so if you will put here, what you will get, that is a 6y minus 6y, and this one is the plus 6y, so it will be 0. So this is the concept. One very important question. So if you want to take a screenshot, you take a screenshot of this. Now one also very important question, you take a screenshot of this question, and solution I have, you also take the screenshot of solution. A non-viscous incompressible fluid flow between the wedge shaped walls into a small opening as shown in the figure. So this is the question 6, and the solution is this. So minus 3 pi, that is the option number D will be the correct, and the very well explanation is there. You have taken the screenshot of this solution?
yes, sir.
Okay. Now the question number 8. A flow field is defined by the stream function. You know already the stream function. Why we are using the stream function? Because of the reduce the dependent variable. And considering the set of streamlines, this that is a streamlines 0, stream second one is the 2 meter square per second, and third. And what is the velocity of fluid particle at y is equal to 1 meter on the streamline, this second streamline. So I have not solution for this question, but if you want, I will discuss in the next class, and with I will come with the solution of this solution question. So one, I have very important slides. You take the screenshot of this important Your, I think from up to that we have discussed. You have taken the screenshot of the stream function or not?
Yes, I've taken.
Yes, if you take a screenshot of this also. Here one line is written in the blue, it is very important. The difference in the value of 5 from one stream to another is equal to the volume rate per unit width between the streamlines. So it is important. Sometimes it will come directly in the examination, some competitive examination also. You take the screenshot of this, how we can drive this. This is the explanation is there. Now the value of phi increase to, this is given. The compressible stream function, you take the screenshot, and also the differential linear momentum equation, that is the Cauchy's equation, how we will derive the Cauchy's equation. So this is given here. Derivation using the divergence theorem, how divergence theorem is applicable for derive the Cauchy's equation, and the derivation using the integral volume concept. Volume concept is also, and one concept here also, the Newton's second law. Using the Newton's second law, how we will calculate, how we will derive the Cauchy's equation. So here the three approach is there for derive the Cauchy's equation. One is divergence theorem, second one is the control volume, and third one is the Newton's second law. So this is the final equation of the Cauchy's. You can take a screenshot. Now the Navier-Stokes equation we'll discuss, I think, in the next class. I think week 10 is about the Navier-Stokes equation. So if you want to take the screenshot, take, you just read, you will get the why we need the Navier-Cauchy's equation is there, what was the limitations of the Cauchy's equation, and that limitation overcome by the Navier-Stokes equation. So it is, if you go through the one line by line, you definitely feel some confidence in this chapter. So that is the differential analysis of fluid mechanics. You take the screenshot of this. So this is the last one. Oh yeah, this thing is done already. So Francis, about your doubt, I will discuss in the next class. I will go through this week your doubt, and one by one the clarity. I will make the slide on your doubt also, because your doubt will help some another people also who is joining, or if see the later this video, that will also help of that guy.
Okay, sir.
Okay, so but I think Pitot to concept you're clear, right?
Yes, sir.
Okay. So Pradeep, if you have also your doubt, you can like yeah, Francis send me one file. Francis, you have, I think, how you can written this, like you send me the picture, no?
Sir, actually, it was done using a notes. There was an app called Notes in the phone. I just instead of typing, we can say, and it will directly write. And just we just need to edit it and take a photo. If you want to include in that, I think the Google Notes also support that thing.
Yes. I have used. I have used. If we talk, if you something tell, then it will be support.
Yes, but I actually I did it to using the there was an app on the phone, Note. I mean Realme Note.
Okay. But Pradeep, if you have doubt, you make your Word document, or let's you send me the PDF of your doubt if you have, because
Yes,
yes, whatever doubt from beginning to up to 9 classes, or maybe the another, if you having, then you just send me your doubt, because as per your doubt, I my also concept and clarity will increasing day by day. So please, if you have doubt, you send me on my.
Yes.
I think you have my mail ID, no? Francis
Yes,
is
sir.
sending me
Yes.
on mail ID. So if you
Absolutely.
have, then you send me.
Yeah.
Okay, then we'll meet on the next class. Okay, bye bye.
Bye, sir. Thank you.
Okay,
Thank you, sir.
okay, thank you.